June's presentation is called Logging of the Chalk Beneath Central London, Observations and Examples from Underground Construction Supervision. And it's being given today by Glenn Hughes of Mott MacDonald. So over to you, Glenn.
Cool, yeah, thanks for that. Yeah, so when I wrote the title, I hadn't actually got the permission from Tideway to do it yet, so it was a bit ambiguous. But now Tideway have quickly come on board and said, and also CVB, the Tideway East contractor, said, yeah, go ahead and do it. So these are my experiences and observations from Tideway East. And I'm not a chalk expert myself, but like most geologists, find it fascinating. But then I realised I'm giving this talk to the southeast of England, which is the global leader of chalk. So there's probably many chalk experts on the line. So some comments afterwards would be appreciated. Thanks. All right. So contents of the talk. I'm just going to introduce you to the Tideway East locations and its setting. Tell you a bit about the local geology and structure. Some of the GI and construction supervision records we made and have available. A bit of the 3D modeling we did pre-construction to help us with our construction supervision. Some of the tunneling and considerations and limitations we experienced. And also some of the chalk features and observations between various Tideway East sites. And I'll finish off with presenting some correlations with the chalk stratigraphy and structure, and also talk about a construction issue at Deptford shaft, which involved the chalk. So just the acknowledgements to start off with. Obviously, Tideway and CVB, Costain, Vinci and Bashi contractor for giving me permission. Rob, Ed and Chris from Mott MacDonald, who provided some of the construction supervision records and also reviews. Martin Stanley, CVB, who also provided some of the records, and also Mr. Tideway himself, Tim Newman, who was always on by to give us some helping hand and also some records as well. So I won't be talking about the geotechnical design at all, but there is a paper come out recently on the design of the geotechnical structures for Thames Tideway Tunnel East. Various authors there from the contractor, Mott MacDonald as well as the designers, and also Tideway themselves. So if you're interested in seeing some of the innovations they did on construction, that's where you should head. All right, so Tideway East. So Tideway has been around for a few years now. Many of you are probably familiar with it. It's a 25k tunnel from Acton to Beckton via the Lee Tunnel. It's also got a couple of short connection tunnels at Frogmore and Wandsworth, and also Greenwich. At 7.2 diameter, 10.2 meters diameter is the main tunnel, about 30 to 60 meters deep beneath London. There's 3 construction contracts. There's a west, takes you up to about Battersea. Then there's a central section, takes you through to about Tower Bridge, and in the east. I'm fortunate to have worked on all 3 sections at some stage, involved with tendering for the west section, ground investigations for the central, and construction for the east. There's 6 TBMs, and if you want to track where they are at the moment, there's a good website here. Just search Tideway TBM tracker. And completion date is 2025. The feature of the tunnel is it's designed to pick up these shafts, which are the connecting into the main sewers through London. And obviously the tunnel is going to act as the super sewer, taking all the muck out of the River Thames down to the treatment plant. So simplified Tideway route geology. So in the west, largely encounters the London Clay Formation. Through the central section, it transitions through the Lambeth Group Thanet Formation. And in the east, we're starting to hit the chalk, and the TBM will the tunnel will hit the chalk somewhere around sort of Tower Bridge area. And hitting the chalk in the east section, the combination of the chalk level rising up and also the tunnel getting deeper as we go along. Right, so I've got 5 main Tideway East sites I'm going to talk about. And they've all got these unique codes. You may see them on road signs around London. You have to excuse me if I sort of talk, I call them KEMPF, CHAWF, EARPS. Yeah, it's something you just get used to, but we got King Edward Park over here, Chambers Wharf, Earl's Pumping Station here, Deptford Church Street, and Greenwich Pump Station here. And this is the Greenwich Short Connection Tunnel coming into the main tunnel drive here. The Tideway East starts at the Chambers Wharf, which contains a deep shaft, a TBM reception adit from the central section, and another TBM launch heading out towards the east. And Chambers Wharf also acts as a reception for the Greenwich Short Connection Tunnel TBM. And then at King Edward Park and Earls Pumping Station, we've got shafts with intersecting the tunnels there. And we can see here that in red, most of the construction has been completed on the shafts and adits. In progress at the moment is the main tunnel drive east from Chambers Wharf, and also the main tunnel drive or the secondary tunnel drive from Greenwich towards Chambers Wharf. And there's also a small connection adit at King Edward Park that's in progress. So just touch on the structural geology within the Tideway East section or the East London section. So there's some work done by Mortimore et al. In 2011, where they looked at the assessment of some of the major linear construction routes and delineated some of these structures. So the main features we've got are the Greenwich Fault coming through here, which almost intersects the Greenwich pump station down here. And also the Millwall anticline, which is about midway between the Greenwich tunnel here and also the London Bridge fault zone, which is just to the west of Chambers Wharf. So the solid geology from BGS, we've got our two features here. We've got Greenwich fault zone and Millwall anticline, creating these sort of chalk highs within the bedrock. We've got Lambeth Group and London Clay Formation further towards the west. Because we're tunneling at depth, the only structures intersecting these other solid units are the shafts going down, but the tunneling itself is firmly within the chalk. So just an overview of the chalk stratigraphy we've got in East London within our sort of construction zone. So again, there was some work done by Mortimore et al. In 2011. Sort of correlating boreholes from some of the main construction projects with chalk pits around the sort of periphery of London. And they sort of figured out that most of the chalk stratigraphy underneath London is the sort of Seaford chalk, loose nodular chalk, and coming down into the lower sort of white chalk subgroup. And actually due to the sort of prevailing depth of construction in London, most of the construction actually takes place in the East London within the Seaford chalk. And we've got these three subunits here, the Havenbrow, Cookmere and Beltout beds. And superimposed on these beds, we've also got some of these marker beds, which we keep an eye out for, such as the Bedwells Flint, Seven Sisters Flint, Shore Mile, which is the contact at the lower of the Beltout bed. So these are key marker beds, which are useful in delineating these units. And we can also trace the chalk stratigraphy back to Seaford itself to see how it looks like in the cliffs on the south coast. So we're expecting Tideway East to be mainly excavated in the sort of Havenbrow and Cookmere beds. And there's some descriptions here. So the Havenbrow beds are generally white chalk with some mottling, and we've also got fossil shell fragments in the underlying Cookmere beds. The fossils are largely absent. Between these beds, we've got potentially three large flint bands with these unique names, such as the Bedwells Flint, the Michael Dean Flint, and the Seven Sisters Flint down here. And what's unique about these three units is we got these closely spaced, clean subvertical joints, which are quite characteristic. So that's something we'll be keeping an eye out for in our construction supervision. And also sheet flints and inclined conjugate joints may also be present. And just some reference photos of what some of these marker beds look like. So we've got top left and bottom left, we've got a few marl beds, marl seams here, forming boundaries between some of the chalk units. And then we've got some flints on the right, and this is one of the Bedwells columnar flint bands from the Havenbrow Cookmere beds boundary. So when we were describing the chalk at Tideway East, we didn't do anything out of the ordinary. We mainly looked at its strength and density using field hand tests. its color. We looked at the discontinuities. We want to know the type, what it was, if it was a fissure, a fault, orientation, roughness, spacing, aperture, and infill. And all this relates back to, we want to describe the Syria classification, which we could relate back to our ground investigation boreholes and our design verifications. And we also want to look at things like the flint bands and other features, and also the stratigraphic formation and member as well. So we found GSI to be a sort of main classifier for design verification, just because we had the opportunity to look at open face of the chalk, and we decided to try and quantify it a bit by estimating the RQD and also the joint condition rating, and using the plot here from Hook and Marinos, we could come up with a GSI value, and also we could quantify that value and also verify it with observations in terms of blockiness and joint surface condition. And this ended up being quite useful because, as I'll show later on, we didn't actually have the luxury of getting right up close to some of the excavation faces to take a close look at some of the discontinuities. So we used photographs quite a bit to determine spacings and also pervasiveness as well. All right, so just some of the ground investigation and construction records we had. So mainly from the shaft and SCL Adit excavations is where we could do most of our observations. The TBMs and Tideway East are both slurry machines, so there's actually no opportunity to inspect the face of those TBMs coming through. Bottom left here is an example from the Tideway Central where they used an EPB TBM, where they could actually get samples out of the cutter face to verify their ground conditions, but unfortunately Tideway East, we haven't got that luxury at the moment. On the right here is the TBM tracker, so we can see the TBM is actually just left Greenwich and it's just left Chambers Wharf as well. So if there's going to be some information coming from the TBM pass, then that's something we'll probably look at in the future as well. So ground investigation boreholes. So there was a couple of GI phases. There was the client GI phase, and then within Tideway East, we did a sort of a targeted GI phase during detailed design that was carried out concurrently, and there's information on that in the paper by Vance et al. In the Engineering Chalk 2018 proceedings, and that focused on detailed logging of the chalks, the identification of marker beds and the stratigraphic units, and also geotechnical testing for the main design parameters. We had some shaft log construction records, and these were largely undertaken by Tim Newman and some of the CVB engineers. And these are actually quite useful. So there's a hemisphere here, which is actually, it's not a stereo net, this is just the shaft layout. The shafts are nicely labeled with panel numbers, so you can orientate yourself and you can do a little sketch of where you've got your exposures, your sketch on your discontinuities. You can record them down here on the bottom left. Plenty of room for sketches and also photographs as well. So there's a series of these coming down through each of the shafts, which are quite useful to verify the ground conditions. Just touch on some of how we looked at the discontinuities within the chalk. So we have records from borehole geophysics, so televiewer and acoustic records, and we've also got these records from shaft logging. The left-hand image here is from King Edward Park, and this is a borehole geophysics record. You see here we've got quite a few large numbers of these shallow dipping discontinuities in the center here. In the middle here we've got some shaft logging records from Deptford Church Street by Tim Newman. You can see here that we've actually got quite a few steeply dipping discontinuities, probably one set here, the same set, and a couple of different faults here. And at Chambers Wharf, where I was largely involved, I put on the stereo net both the borehole logging discontinuities and also the shaft logging here. And you can see here that without the two data sets, you don't really get the full picture. because there's a bias towards the horizontal discontinuities in borehole logs, which is the way the instrument's set up. And also there's a bias towards vertical discontinuities when you're logging your shafts. And this is because when you're in the shaft, you're only dealing with a flat floor. So you can chip into it with your hammer, and it's quite easy to see the vertical sets, but the horizontal sets are actually beneath your feet. So it's important to use both data sets and also as much information as you can. As construction of the SCO Adits progressed, we were provided face logs. So these are similar to the shaft logs, just a template set up that could be undertaken by either a logging engineer from the contractor or myself or anyone else from the design team. So it allows you to record your geological descriptions, your discontinuities, any groundwater observations, and you can also sketch these on a face as well. So these are quite useful to track progress as we went. Right, so we did some pre-construction 3D modeling using Leapfrog, and this was before construction began, particularly at Chambers Wharf, where I was involved, just so we could realize what we're up against. So Leapfrog's quite a useful tool at plotting on different aspects of your ground investigation data and also your construction sequences. So we could import the CAD models for the shaft and also the adits here. So at Chambers Wharf, we have 2 adits and also a reception coming in from Greenwich. We could plot on our borehole sticks, and we could match up where the top of the chalk was. And in this situation, the adits are about 5-6 meters below the cover to the planet formation. We could further refine the top of the chalk in this area using a series of grouting boreholes that was undertaken by the contractor prior to construction to sort of improve the ground conditions for tunneling. So each of these grout boreholes recorded where the top of the chalk was encountered, and we could use a surface and Leapfrog to accurately show where the top of the chalk was above where we're going to be constructing our SCO adit. And this is useful because we can identify if there's any depressions in the chalk that may cause a reduced cover and inflow problems when tunneling. We could also plot our discontinuity data sets from both our shaft logging and borehole logging. So we could plot these as disks, and from that we could see where they're actually going to be, where the prevailing discontinuities will be intersecting our adits, just to give us a bit of a prediction of what might be happening. And also in Leapfrog, you can do a slice through any of these surfaces. So in this case, we've done a slice through one of the adit faces here, and we can see we're probably going to be getting some steep sets and some horizontal sets and maybe some inclined sets as well. And we could also trace any particular geological features. So this is a small fault that Tim Newman identified in the shaft log. And if you can see it here, we actually imported the shaft log as a PDF, and then we could trace on where that fault was going and where it may be intersecting one of the features at Chambers Wharf. In this case, it was the Greenwich interception chamber there coming through, which is actually yet to be dug, so we haven't found that fault yet. So some tunneling considerations and limitations. So just a few slides with a bit of text. So why are we there? What are the tunneling considerations we're looking at with our construction supervision? So we're looking at the feedback from our shaft and SCO adit logging. The feedback site observations is important, so we can compare this against desk study and ground investigation. We want to assess chalk grade against design criteria. We know the GI boreholes mainly found grade A1 to A3 chalk, so that's what we're looking at. Describe and locate flint bands, which is useful for TBM teeth wear. And in fact, the contractor is looking at introducing intervention events to maintain and replace teeth coming along, so locating flint bands is good. There was potential for driftwood hollows to be identified. So we want to see if any of those came to fruition, had any impacts. None did, although we're only tunneling a short distance from the shaft, and so we may not have had the chance to encounter any. Look for any groundwater inflow from fissures or faults during tunneling that may cause instability of the rock or SCL. Identify any potential stability risks and apply any toolbox measures where required to control stability, such as reducing advanced lengths, changing SCL thickness, or drilling weep holes. And the Adits at Chambers Wharf were actually designed to be free draining, so there were weep holes drilled throughout there. And also we're looking at supplementing tunnel convergence monitoring and SCL thickness measurements, recording where dropouts may occur with the Amberg profiles. So this allows us to track the SCL thickness going forward onto the tunnel. And it was a really collaborative approach, especially at Chambers Wharf. So there were daily shift review group meetings and quality reviews. So we were a key input into those meetings, feeding back on the quality of the ground conditions to the contractor, the designers, and also Tideway as well. So we came up with a few sort of limitations during construction. I mean, nothing ever goes to plan. So also we had a lot of time pressures actually excavating on a 24-hour, 7-day week continuous program. So we weren't actually able to be there all the time to see everything. So we're reliant on sort of site photographs and observations from other engineers. Chalk faces were usually smoothed off using the rotor heading tool, which is the main cutting tool. So we can actually see a lot of features on some of the faces that were just so smooth, the chalk was so tight. Best view we had was actually on some of the benches, because the benches stayed open for longer due to the excavation sequence. We think there's a bit of relaxation, so some of the jointing was opening up, allowing us to see them better. Excavator teeth marks, creating fake discontinuities. So a lot of features on the face, probably caused by the excavator teeth. One of the main ones, due to health and safety risks, we couldn't get right up close to the face. We had exclusion zones in front of many of the faces, and usually wet soft ground due to groundwater inflows and disturbance. So you'd disappear quite quickly if you tried to get up close. We had COVID-19 restrictions through most of last year and ongoing actually. So there's limited shaft people allowed in the shaft at one time. So we really pushed with time not to hold up construction and get in and out as quick as we could. When it came to shaft logging, we actually had limit exposures on shaft floors just because the shaft floor was so flat. So we're quite limited to any sump excavation areas which were possibly disturbed. In the shaft itself, we had compass disturbance as well. So most of the orientations were estimated using panel numbering and excavation drive directions. And the main limitation we had was we couldn't do the full rock mass rating of a face. And here's where our tools such as GSky main came into one of their sort of main useful areas. So just some photos here of plant use and some of the exclusion zones. You can see that on the left here, we've got this rotor tool going around, actually smoothing off the face. Not a lot to see in the cuttings either. Some of the other health and safety risks, we had air quality, overhead lifts and slip, trips and falls. So you had to be quite on to it when you're down there. This is some of the sprayed concrete lining application and some of the exclusion zones. So again, somewhere you couldn't get up close and actually didn't need to anyway because the SCL was covering everything. A couple of photos here of one of the shaft excavations at Earl's Pump Station. So you can see the left here, we've got this just coming into the chalk beneath the Thanet Formation here. And then on the right in the Seaford Chalk Formation, and you can see the flat topography here in the base of the shaft. So there's not a lot to log, and it would be disturbed as well with all the machine tracking. And where you could find material to log, it was possibly disturbed, and you actually had to pick up every bit of information you could, no matter how trivial. So you just recorded flint sizes and defects in the chalk where you could. All right, so I'm just going to run through some of the Tideway East sites and what we found. So this is Chambers Wharf, and this is where I was largely involved. This is the so this is where the TBM swap over from the central to east, and it's a complete TBM swap out from the EPB to our slurry machine. So the two Adits we had were codenamed MNTLC and MNTLD, and this is the tunneling direction coming in through here, and also the Greenwich TBM would be coming in here at a later stage. So we had a 60-metre deep shaft at Chambers Wharf. A shaft geology mainly from the ground investigation boreholes. So we got the sort of limited number of superficial deposits in London Clay Formation, and then we're into the Landworth Group and Thanet Formation coming in through here. We did pick up the Bullhead beds, and then down at the shaft floor and also at our tunnelling level, we've got the chalk of our Havenbrow beds, Cookmere beds, and Bowtout beds. And within the ground investigation boreholes, we also identified 3 main flint band markers, so the Bedwells, Michael Dean Flint, and Seven Sisters Flint. And also the Mid-Lambeth hiatus was also quite a prominent layer in most of the boreholes, and even in the Grouting boreholes as well, but that was higher up. So I'll focus on MNTLD. So this is the launch at Chambers Wharf. So we've got about 5 metres cover to the Thanet Formation here. Expecting most of the Adit to be excavated in the Havenbrow beds. Bedwell flints are somewhere up just above the centre line here. Michael Dean flints comes in somewhere just down the bottom based on what we had in our ground investigation boreholes. The whole Adit itself is about 10 metres diameter, and it's about 23 metres long. So these are some of the, actually I'll just go back. So one of the features to excavate the Adit, it's not due to maintain stability, it's not a clean excavation all the way through. We have things called top headings, benches, and inverts, and these are numbered sort of sequentially, telling you what stage to do. So we do top heading 1, top heading 2, then we come back and do the bench, do another 2 top headings, come back and do a bench, and so on. And actually the inverts are done towards the end. So it's a bit of a piecemeal process going through. And after each stage, there's a spray concrete lining layer applied, which is sacrificial and dug out before the next stage. So these are some of the images of what we had of a top heading, a bench, and an invert. So top heading on the left, we've got quite a few flint bands here. Some flint bands are blockier than others, more persistent. We've got things like a short double flints here, another double flint here. The chalk face itself is quite tight, not a lot of information on discontinuities from a distance, quite smoothed off by the rotating tool. On the bench on the right here, you can see we've got some horizontal lines coming through, some horizontal discontinuities, probably opening up with a bit of relaxation. I've got a nice big flooded area in front, so it's going to restrict our access getting up close to that face there. Down at the invert here, I've got more flint bands coming through. It's a bit blockier, so it's a bit easier to see the discontinuities here. So somewhere we might get a bit more information. Due to the sort of pre-construction grouting, the grouts managed to infill some of the chalk features, making them stand out a bit better. So this is a prominent subvertical discontinuity coming in through here on top heading 7. And actually, if we go through 10 meters difference, so this is top heading 17, we can see we actually managed to trace this discontinuity across the face. And here it's just sitting just to the left of center. So this is useful. It gave us information on its sort of strike and dip direction as we could trace it across. Again, we've got this, the flint bands haven't really changed elevation coming through, so they're actually quite horizontal. We managed to trace the same flint bands all the way through. Some other features we've got these little vertical dark patches, and these are actually grout tubes from the grouting that came down from the surface, so not flints at all. So they can be a bit misleading as they're similar shape. There's another grout tube coming in through here, and you can see up here these are some tunnel convergence monitoring prisms which get installed. It allows you to monitor what the tunnel shape is doing. At Chambers Wharf, we encounter one fault, which is nice, something a bit different. So this is bench 14. We got the fault right in the corner. This is a normal fault on this occasion, and the flint bands are offset by about 200 to 300 millimeters, so not a lot of offset there. The fault was infilled with grout, so it shows that our grouting from the surface did do a job at filling in some of these structures, potentially reducing groundwater flows there. As we come across, so we're at TH23 now, which is about 4 meters beyond bench 24. We can see our fault coming in through here with our offset of our flint bands, and the fault's starting to migrate its way across the face. So again, this is allowing us to get an idea of its direction of dip and also its strike. And this is the head wall of MNTLD, so this is right at the very back. And we can see that the fault coming right down through here, right down through the invert as well. And if you remember, at bench 24, the fault started right in the corner, so it's migrated its way across. So in plan view, and this is part of the sort of as-built construction supervision drawings we did for Chambers Wharf. You can see the fault trades coming in through here. This is the strike starting at bench 24, ending up at the head wall, and also it's dipped there about 45 degrees towards the southwest. And this is the other prominent discontinuity that was infilled with grout. We actually picked it way up at top heading 20, or top heading 2, and traced it all the way to the head wall. So it gave us an idea of its strike, and also the dip, which is 85 degrees towards the southwest. And then we got the other things like our flint bands and our bedding, which are actually dipping much shallower towards the east-northeast. And this, the discontinuity, the steep dipping set, which we're calling set 1, also matches up with what we had on our pre-construction records. So our shaft logging here, and also the bedding dip and dip direction matches up with what we had in our pre-construction borehole records. So it all sort of matched up nicely on this one. We also did a long section as-built profiles through MNTLD and also MNTLC, showing the location of the flint bands, of a key showing either continuous or discontinuous flints, relative flint size, levels above and below tunnel centerline or tunnel axis. And we've also had a go at trying to correlate these flints to the marker flint bands. So it's possible Bedwell's flint somewhere up around here at 53 meters ATD. There's a double flint just below it, and we possibly picked up the Michael Dean flint down at the bottom. So a few more sites. This is a site done by my colleague Ed. So Greenwich Pumping Station contains about 50 meter deep shaft and also a TBM launch at it, which heads towards Chambers Wharf. So this is some of the features that were in the adit at GREPS or Greenwich Pump Station. So again, we had grade A chalk was observed. We've still got a couple of flint bands here, although not as many flint bands as what we had as Chambers Wharf. And again, we've got the main discontinuity sets. So we've got some steep dipping discontinuities, some sub-horizontal, and also some inclined sets coming in through here. It's close up on some of these discontinuities. So this is an inclined joint coming down through one of the benches here, and it's possibly filled with grout. And you can see the grout tube coming down and ending here. So again, this is where the pre-construction grouting really paid off and possibly sealing up a groundwater inducing feature. We had some further faulting at GREPS, and also this is a much larger fault than what we had at Chambers Wharf. I think the offset was somewhere in the order of 1 meter. It actually didn't cause any construction issues on this occasion, but it was a good find, something good to note coming in through here, and you can see the faulted block coming in through here. Some other observations from Greenwich, and these are to do with the grouting that was undertaken there as well. So you can see a big grout tube coming in through here. Kind of looks the same color as a flint, and there's also grout pockets in here as well. And in particular, in the ceiling of the top heading, we've got these 2 dots, which also look like flint bands, but they're actually the trace of the vertical grout tube that came down. So it's something that can be a bit misleading, but you have to sort of keep your eye out for anything that could be not natural. So again, this is one of the as-built long sections we did at Greenwich, and we've got our sort of a main flint band coming in through here, which is the possible bed wells flint, at a similar level to what we had at Chambers Wharf, around sort of 53 meters ATD. Michael Dean flint is not so prominent if it was present, somewhere down at this level. And then we've got this fault coming in through here, which dips sort of towards the east. So King Edward Park is the last of the sites I'll talk about. This is, I guess, further down the line of construction. So construction's not advanced here. The shaft is almost completed, and there's a short connection at it to be dug, which will intersect the main tunnel drive from Chambers Wharf. So I was in April, I was fortunate to inspect the base of the shaft on one occasion. Again, we had the same problems we had at some of the other sites with not a lot of chalk topography around. And in fact, the only bit of chalk I could see was a possibly disturbed, dirty section near the sump, which I couldn't actually get up close because of the soft ground in front. So I had to sort of estimate some of the discontinuity orientations from a distance and record these on the photograph and take measurements using a compass and orientated with the panel numbering, because my compass would work down at that depth. So on the left here is the sort of plan view of the shaft. It's not the stereonet, the stereonet's on the right. So this is the sump area here, and these are the discontinuity orientations I mapped. So we've got a steep one going out towards the southwest, which also matches what we had at the other site. We actually got our bedding heading out towards the northeast, a shallow dip, and then we've got an incline set coming out towards the southeast. And these actually matched up quite well with our pre-construction borehole information. So we've got our steep dipping set up here, our bedding here, and our incline set over here and over here. All right, so what does all this mean? So we're looking at trying to correlate some of the structures between the Tideway East sites. So this is a map of mainly the Tideway East area. So we've got the Greenwich Fault and the Millwall anticline, these main features, and also the London Bridge Fault Zone. And these are our sites here. So the red ticks are the faults. You can see here we've got a couple of faults dipping in a sort of similar direction with the London Bridge Fault Zone. So it's a bit of correlation there. We've got green ticks are our bedding. So we've got our bedding doesn't really get above 5 degrees. And there is a slight change in bedding direction either side of the Millwall anticline, although the Chambers Wharf bedding doesn't match that setting as well. It's more of a regional dip bedding over here. And then the blue markers are probably our smaller conjugate discontinuities. So these are forming at about 90 degrees to each other. And then the black one is this main southwest dipping, steep dipping discontinuity set. And this is what we think could be the main set within that Havenbrow and Cookmere beds, which we can see or traced over much of sort of southeast. So we've got a bit of correlation work in progress in this area, but it seems to be some matchups here. There has been some recent paper published by Tim Newman and Hadlow, and this I think this is probably available now. So he's actually looked at borehole positions along the Greenwich Tunnel route. So this goes all the way from Greenwich to Chambers Wharf, and he's actually matched up the stratigraphy and bedding directions quite well, and he's actually mapped out in good detail this Millwall anticline. So you can see the chalk units actually rise up. So the tunnel itself will actually, even though the TBM is about here, it should encounter most of the Seaford chalk formation and into the loose nodular chalk. And some of our bedding directions, especially at Earls Pump Station, match up with the dip directions on these features. So I'm just going to spend the last sort of 5 minutes or so talking about a chalk-related construction issue. So this is it's been mentioned before. There's a Cooling Prize paper by Emily Riley out, and also Martin Stanley included it in his talk at the 2020 GE Basements Underground Structures Conference, and you can see that talk online if you're interested. It's a very good talk. Talks about all the other Tideway East sites. So this is at Deptford Church Street, so it's located near the Greenwich Fault Zone, somewhere around here. So there's a potential for high groundwater flow and fissures in the chalk due to the faulting. There's limited fissure information in the borehole logs, and also they did do a pump test at this location, but because there's a limited discharge and the fact that they weren't allowed to disturb the groundwater levels too much, they actually couldn't max out the pump test to get a good idea of what groundwater was doing. The geophysics found a inclined fissure dipping about 70 degrees northeast that was extending beyond the shaft base, and it is quite a large feature. It was found in several boreholes. Some follow-up targeted packet testing and the pump flow meter testing indicated that there's actually high groundwater coming from this fissure. It was about 90% of the total flow. So it was something that had to be investigated in action. So there was some targeted ground investigations around the outside of the shaft to try and constrain that fissure's location. And what it led to was some pre-construction fissure grouting completed by Bashi using their computerized grouting software and system. And then to make sure they actually grouted up to improve the construction, there was some post-DEWAL construction validation as well. So the shaft to be sunk at Deptford Church Street was using DEWALs. So prior to constructing the DEWALs, there was a perimeter of boreholes around the outside to obtain geophysical data on the fissure orientation. And this data was concurrently fed into a leapfrog model, which is shown on the left. So the discs are showing where the fissure was located and also its orientation. And in the background, you can see the shaft. And actually, about half the fissure was dipping down 70 degrees, and about half the base of the shaft was either side of the fissure. So something had to be done pre-construction to try and reduce any groundwater impacts on construction there. So grouting was done from the surface over an array of areas, and you can see the image on the right here. This is a sort of post-grouting, post-construction validation borehole coring, which found the fissure to be successfully grouted up. And I understand the grout was actually tested in the lab to make sure it was actually grout and not some sort of other material that was present. So it goes to show you that it was a good sort of chain of events here to pick up a construction hazard and mitigate that hazard and also prove that it worked. Right, so last few minutes, just going to summarize what I've talked about. So construction supervision. So I guess as geologists, we don't always get the ideal situations to carry out what we'd like to do. So we could have access constraints, unable to carry out our full geological classifications. And sometimes you have to fit in with the construction programs as well. So quite often you're in and out between events, trying to get the information you need. And on this job, we had sort of reduced site visits and access, which meant the use of site photographs was also important to assess things like GSI. Design feedback. So feedback from site observations is important to compare against the design assumptions. So in this case, the geological investigations and logging at Tideway East, we pretty much validated to date what we've expected the ground conditions to be for the shafts and SCL Adits in the chalk. So it worked out quite well. On the occasions, we've identified variations where the ground conditions needed revised construction methods, such as the Deptford Church Street grouting. And one thing that worked well was the pre-construction grouting for most of the features or most of the adits along the alignment proved to be quite successful in reducing, well, closing up some of those features and probably reducing the magnitude and associated risks of uncontrolled groundwater flow. Summary-wise from geology, so what we identified in logging was a greater number of incline and subvertical discontinuities, which weren't evident in the GI boreholes or geophysics. The dominant subvertical set evident in the Havenbrow and Cookmere beds from published information can be traced across most of the Tideway East sites, and this is at 80 to 85 degree dip towards the southeast. We've got additional joint or joint sets, possibly conjugate apparent to around 90 degrees to that subvertical set. We have marker beds were identified in the GI boreholes are useful, but as we've seen, flint bands are very common throughout the chalk. So probably a bit of further work to try and correlate those flint bands if we wish. Faulting of a limited throw was expected at frequent intervals throughout most of the Tideway East sites, and this was observed. We did have concerns about major faulting within the Greenwich fault zone at Greenwich, but luckily this wasn't realised. Faulting was present, but it was much more minor than expected, so that was all right. And bit of work in progress is we're going to try and do some more work to correlate some of the structural geology features between the Tideway East sites. There's a lot more information from the ground investigations and construction that we can feed back into that. So that's a work in progress we're going to be looking at going forward. Yeah, that's it.
Thanks, Glenn. Does anybody have any questions?
Hello, Glenn. It's Felicity. Thank you very much for that. That was really interesting. I noticed on the face log records, in the bottom right-hand corner, there was a little QR code that said "Scan me." Just out of interest, what's that for?
I'm not sure, actually.
Oh, okay.
Well,
Didn't know if it was part of like a data management process or
so
yeah, is that for the client use or I wasn't sure.
This one here. All right, yeah. No, I might check that out. Actually, these face logs were provided by the subcontractor Shotcrete, but obviously it's got a Tideway logo next to it. So, well, that's a Shotcrete logo in the ScanMe, so it might be something they use, which would be quite useful, I guess.
Okay, thank you.
No worries.
Hello, Glenn. It's Colin Warren here. That was quite good. I noticed that, those joints are similar to what we encountered at Swanscombe, actually. I think we had west, northwest, east, southeast major joint set one. I see they slightly going northwest, southeast in your structural pattern. But that's quite interesting, really. I suppose it'd be good to try to collate all that because, it's nice to get some joint information in London. And I've always wanted to try to see if the problem with the London clay is people talk about joints within the London clay, but nobody seems to get any directions. And I suppose that's because they're so curvy planar. So it's but it's good to see that we're getting some information from a geology that's actually buried.
Yeah. I mean, one of the few things we could measure, so it was good to measure as many as we could, and then try and piece them together later.
Yeah.
Yeah. All right. Any other questions, I guess?
Sorry, I had a call.
Hello, Glenn, it's Martin. I've got out of my ICA meeting.
Oh, yeah. Yeah.
I just wondered, did you think about correlating with the mole bands as well as flint bands?
Yeah, actually, the mole bands were quite traceable as well. So, yeah, that's something we can look at, especially the Shore mole was a bit of an easier find. Although I think at the levels of adit construction, at least, we didn't get any mole seams, but they're definitely in the ground investigation boreholes that went a lot deeper. So we can, and I think on Tim Newman's picture here, he might have a mole seam, or he's got the Bedwell's flint trace through.
If not to interrupt Glenn, sorry, I said Russell here, so I'm Glenn's colleague and worked
Right.
on this side of things with him. Just to be clear on that, so we in the great GI investigations, we did send most of the holes down, so we actually could find the Shore moles because we were convinced that we could use those as a better marker overall in terms of tracing across the sites, and that was pretty useful at all of these locations to give us some feeling for the kind of faulting offsets in and around the shafts before we looked there, and then we looked at the flint observations within the adits because that's what was available to us. But yeah, the Shore moles are a very good persistent marker across here that can be really useful for you in understanding what your potential offsets might be.
Thank you.
Can you tell us about the progress of the actual TBMs? I mean, what are they actually doing per week? Do you know that?
I forgot to the TBM checker. I know I think the TBM that just left CHAWF might not be doing much at present while the work carries on at King Edward Park, which is the next stop for it. But I think the TBM from Greenwich is well on its way, but I'm not sure what the rate is on that. And I think the TBM tracker gets updated weekly or 2 weekly, something like that.
Okay, and they're both slurry machines, are they?
Yeah, both slurry machines.
Okay.
Yeah.
We've got a question in the chat from Steph. Did you apply a confidence to some of your interpretation? For example, those faces you can get up close to and had to interpret from photos.
We were a bit sort of cautious on things like GSI, which I can get up to it here. So we used a range such as like the joint condition rating. We used a flow system to try and come up with what that rating was. So we used a range there rather than trying to pick a high or a low value. And then also we for the sort of RQD, we weren't sort of overly optimistic on what the spacing was. We tried to keep the spacing sort of quite close together, but in most cases, our design GSI was quite low. It was around sort of about 56, and we're always well above it. And I think towards the end of one of the Adits, it might have been MNTLD at Chambers Wharf, we actually increased the advanced length by 0.5 meter just because the chalk was even better than what we thought. So it was quite useful like that.
Why did you use the GSI? I'm just interested in why you go to GSI. I mean, are you trying to get a rock mass parameter or?
I can take that, Glenn, if you want.
Go for it. It told me to.
So so I guess the real reason behind it was we effectively built up a rock mass classification at the start from all of our ground investigation boreholes, etc. And the conceptualization of what we were going to expect to see within the chalk was effectively a close space joint set within the Haven Brow, the bedding, and a couple of conjugate sets where, looking at the scale of the tunnel, we were believing that we could apply GSI, and we thought that was the way to go. So in discussion with the tunnel designers, that's what they decided to design off. So in terms of that, it was interesting. I mean, it come through from the stuff that's Glenn there. I mean, there's the restrictions that you get within SCL and the other things in terms of the actual access to the face. it sort of lends itself to a quick assessment. Like, I'm not advocating that you shouldn't get up at the face and look at these things and assess the joints, but we had a good feel for the chalk based on all of the core logging and other things that we'd done beforehand. The contractor who's doing the tunnel is kind of experienced in terms of understanding what's there and feeding back to us on the stability in the other side of things. So after seeing a few faces within a limited advance, you get the confidence that, you know, that things are as you expect them to be. We're not having anything untoward, and we progressed on that basis. But it was really, you know, we, based on the number of joint sets, the closely spaced vertical set and the bedding and the other joints at the scale of the tunnel, we felt it was the right thing to use, and we applied it through the construction that way.
Yeah, I still don't think they would probably understand GSI at the face anyway. But I understand that because I have tried to use it to get a parameter, and what I've noticed is the parameters you get from it is not borne out by the laboratory testing. So for the chalk, you know, looking at the GSIs I've got, I mean, they predict like phi dash of 28 degrees when the minimum you get is about 32 degrees. So, yeah, I don't know. It's one of these things that rock science, you know, I suppose it's all based on so many different types of rock that it's an averaging technique.
Yes.
So I don't know. I mean, I'm fairly happy with the Syria grading, and you know, I mean, I know in this chalk, you know, being beneath the Thanet, you always expect structural chalk. You probably go with a 1 to 1.25 spacing in advance, or something like 1.5 spacing at max. But you know, I suppose it depends on what people want to do. Oh, who sets the spacing? I suppose that's done by the NATM engineer in the field. Is
that's it? Well, by it effectively, there's a design advance that based on their assumptions, and we're validating against what they've assumed it to be. And as long as things are that good, they continue that advance. Otherwise, if we'd have found worse conditions, then there would have been a feedback loop that would say, you know, we recommend a reduced advance length on that basis. Yeah.
Mm.
Is there any more questions for Glenn? No. Okay, let's give Glenn a huge round of applause for that talk. I really enjoyed it, so thank you.
Thank you very much.
The talk has been recorded, and I will be putting it on YouTube, so please do tell your colleagues and friends. Our next talk will be given on the 20th of July, and that will be on the Lower Greensand Seaway of Northwest Europe by Martin Wells from BP. So please do join us then. Thank you all for attending, and have a good week.
Thank you.
Thank you.
Thank you very much.
Thank you.